So we're in section 9.5 today. And we're talking about secant, tangent, and chord lengths. Check the airflow. Okay? All right, so we're talking about secant, tangent, and chord lengths. So we have four different combinations that we're going to talk about, depending on whether we have a secant, a tangent, chords, and where they intersect. So I'm going to give you the theorems, and then we'll draw a picture. I'm going to make the pictures match up to the pictures inside your flip book. So the important information from today is to understand what the theorem is telling you, but get the relationship, get the rule into your flip book or into your notes, and then follow along with the examples that we do. All right, so our first combination is going to be for two tangents. And this picture is at the bottom of the third page of your flip book. So our theorem for two tangents. So we're going to say if two segments are tangent to a circle from the same external point, their lengths are equal. So let's draw our picture so we can see what this is telling us. So here is our circle, and again, this is on the bottom of the bottom of the fourth page on your flip book, and our two tangents. So here are our tangents. And here's our other tangent. And here's the point, here's the external point where they intersect. And we'll call that point V. And this tangent point is point A. And the tangent point down here is point C. What this is telling us, and on this, I would not worry about what the way that the flip book is marked. I would write down what we write down up here on the board. So what this is telling us is that the length of AV equals the length of CV. The length of this segment here is the same as the length of this segment here. So we have two tangents from the same point outside the circle. Their lengths are the same. Anybody have an idea of how we might go about proving this? What was our hint at the beginning of the unit if we didn't know how to solve a problem with a circle? Draw in a radius. So I'm going to draw in two more radii. So here's one. Here's another one. And I'm going to make this into two triangles. What angle does a tangent and a radius make?
Right.
A right angle. So this is 90 degrees here, and this is 90 degrees here. What do we know about the lengths of every radius of a circle? Are they the same or different? Same. So those two segments are congruent. This segment in the middle here between these two triangles is congruent to itself. So these two triangles are congruent by hypotenuse leg. So the two triangles are congruent, so these lengths have to be congruent. So there's a quick proof of why this works. Drawing another radius, divide this into two triangles. Circle problem turns into a triangle problem.
Isn't that always how it works?
If we have two tangents, yes.
Okay.
All right. So two tangent segments, if they're tangent to a circle from one point outside the circle, their lengths are the same. So that's our first rule. Our second rule is for two secants. So let's go to that rule. So our rule for two secants tells us, this one's a little longer, if two secants intersect outside a circle, two secants intersect outside the circle, the product of the length of one secant segment with its external segment equals the same product for the other secant. So let's draw a picture to see what this is telling us. So this is our theorem. So here's our circle, and I'll make it look like, and this is on the bottom of the next page of your flip book. So not the top one, but the bottom one. And I'll try to make it look like our flip book. So here are our two secants. Here is one, and here's the other one. And this is point V. And we'll label our other points. We have point A, C, B, and D. What this is telling us is that the product of the length of one secant segment, so the length of this secant segment tells us that BV times the external segment times AV equals the same product for the other secant. So the entire segment, dV for the bottom one, times the external segment, times CV. So the length of this whole segment times the length of this little piece equals the length of this whole segment times the length of this little piece. So this is what you should write in your flip book. Don't worry about the way it's labeled. This I think is going to make more sense. And my shorthand for remembering this is that the whole times the outside equals the whole times the outside. So the whole piece of this segment times the outside part equals the whole piece of this segment times the outside part. That's what our theorem tells us about two secants. And remember, notice that our secants are intersecting outside the circle, and that's when we can figure this out. Questions on this part? All right, let's look at an example of calculating with this. So here's our example. Our circle. There's our circle and our two secants. And for this one, we'll label the parts, we'll label the points X, B, C, A, and D. And we know our problem tells us that AB is 13, BX is 6, DX is 15, and XC is what we're looking for. So we have two secants. They're intersecting outside the circle. So our rule that we're going to use is the whole times outside equals whole times outside. So let's label the parts we know. AB, the length of AB, this segment is 13. The length of BX, this little piece, is 6. The length of DX, this whole thing, is 15. And we want to know XC. This is question mark in here. So let's plug into our rule. For the top segment, for AX, what is the length of the whole thing? 19. This part is 13. This part is 6. So the whole thing is 19. So 19. And what's the length of the outside part here? On the top one, 6. The whole part of this segment, dx, it tells us it's 15, times what's the outside part? Question mark. So we'll just put a question mark in there. And we're going to solve for question mark. 19 times 6 is 114 equals 15 times question mark. Divide by 15. And I get that the question mark equals 7.6. So the whole times the outside equals the whole times the outside. Questions on the example? Okay. And remember, with our gray boxes, we're talking about lengths, not angles and arcs. All right, let's look at our next rule, our next combination. Excuse me. Our next combination is a secant and tangent. Similar rule, just a little bit different. So when we have a secant and tangent, our theorem tells us if a secant and tangent intersect outside a circle, the product of the lengths of the secant segment and its external segment, just like we talked about before. Equals the length of the tangent squared. So we have a secant and a tangent that intersect outside a circle. The product of the lengths of the secant segment and the external segment equals the length of the tangent segment squared. So let's draw a picture so we can see what this is telling us. And this is on the top of the, see, 1, 2, 3, 4, 5th page of your flip book. So the top gray box on the 5th page. So here is my secant. And here's my tangent. Forgot my arrows on this one. And this point is V. This point is C. The tangent point down here is B. And the other point up here is A. So what the theorem tells us is that the secant segment AV times its external segment times CV equals the tangent segment squared, equals BV squared. So the secant segment, this whole segment, times the external segment equals the tangent segment squared. And the shorthand that I think about for this one is the whole times the outside equals the tangent squared. So this should be what you have written in the top gray box on the 5th page in your flip book to help you remember how this works. Questions on our rule? All right, let's look at an example. Okay, here's our circle and our secants, our secant and tangent. And for this problem, we'll call this point X. This point B. This point A, and the tangent point is point C. And the problem tells us that BX equals 24. CX equals 30. And we want to figure out AB. So AB equals question mark. Now, our rule for this one is going to be the whole times the outside equals the tangent squared. Because we have a secant and a tangent that intersect outside our circle. So for the top line, for the top segment, what is the length of the whole thing? BX is 24. AB is what? Question mark. We don't know what that is. That's what we're trying to find. So what's the length of this whole segment? 24 times? Plus. We have to add the two lengths. So the whole segment is 24 plus question mark. We don't know what it is. Times the outside. What's the outside segment for the top part? Times 24. And that equals the tangent squared. Well, CX is 30, so the tangent is 30. And I want to solve for a question mark. I didn't use X because this point was X. So to solve this, I'm going to distribute. So 24 times 24 is 576 plus 24 times question mark, and 30 squared is 900. So now I subtract 576. So 24 times question mark is 900 minus 576 is 324, and divide by 24. And question mark equals 13.5. So we found the whole and the outside, multiplied the whole times the outside, and that equals a tangent squared. Questions on that example? All right, our last combination. Let's look at our last combination. Our last combination is two chords. So we'll do like we did before. We'll get our theorem first, and then we'll draw a picture and do an example. Two chords. Our theorem says if two chords intersect inside a circle, the products of the lengths of the segment of one chord is the same as the product of the lengths of the segment of the other chord. And I'm just going to say equals the same product on the other chord. So if two chords intersect inside a circle, the product of the lengths of the segments of one chord equals the same product for the other chord. So let's draw a picture and see what this is telling us. So here's my circle, and this is the last gray box in your flip book. So here are our chords. And notice that this one is different because our chords are intersecting inside the circle. So this is point A, point C, point B, and point D. And we'll call the middle point V. So what this theorem is telling us is that the lengths of the segments of one chord, so AV times VB, that's the lengths of the segments of this chord, the product of the lengths, equals dV times VC. So this piece times this piece. And my shorthand here, the way I remember this, is the part times the part is the part times the part for the other chord. Part times part equals part times part. So we're just dividing, the chords are divided into parts. We multiply the parts of one chord by the parts of the other chord, and they are equal. So this is what I would put in the flip book. I wouldn't worry about the way it's written in there. I think this is going to be easier for you to remember. Questions on the rule? All right, let's take a look at an example using this. All right, here's our circle. And our two chords. And this is point A, point B, point C, point D. And this is, let's call this middle part V. And we know this tells us that AV is 3, VC equals 7, DV is 5, and we want to find VB. So we have two intersecting chords. Our intersection is in the center of the circle, so that tells us we're going to use part times part equals part times part. So let's label our pieces. AV is 3, VC is 7, DV is 5, and VB is what we don't know. Let's call that X this time. So we'll plug into our rule. For this segment, the part times the part is 3 times 7. And for the other segment, the part times the part is just 5 times X. So I get 21 equals 5X. Divide by 5, and X equals 4.2. All right, questions on that example? Let's do one more with this that's just a little trickier. Yeah. All right, so another quick example, and then we'll be done. So for this example, we have a chord, and so here's our example on this one, and we'll call this point D, this point V, this point A, B, and C. And we know that BV equals CV, and those both equal 10. And AX is 3, and we want to know segment AD. This should be AV, sorry. All right, so we have two chords intersecting inside the circle. So our rule is going to be part times part equals part times part. So let's label what we have. BV and CV are 10. Even though it doesn't look like it, that's what the problem tells us. Each of those is 10. AV is 3. And we want to find AD, so we want the length of this whole thing. Well, the rule tells us about these two parts. So if we call this part X, the part from D to V, if we can find X, how do we find AD? If we find this part, this piece here, how do we find AD? Subtract 3. So if we know this part, and we know this part, how would we get the whole thing? Add them together, right? So we're going to find x first, and then we'll add that to 3 to get this whole segment. So let's plug into our rule. The part times the part for this segment is x times 3. And that equals the part times the part for this segment, 10 times 10. So 3x equals 100. Divide by 3. X equals 33.33. So this piece is 33.33. The length of the whole thing is AD, is 33.33 plus 3 equals 36.33 units. Questions on that example? All right.